This is the fifth section of chapter 3, Conic Sections 2, and here we're going to be looking at tangents and normals to our hyperbola. Now, just like the ellipse, there are some results which we can quote without proof, but these results are not in the formula book. These are results that you would need to memorize. But you could be expected to prove these results as well. You could get a question that said, can you show that the tangent is this or the normal is that? Okay, so we'll start off with tangent. Now remember, the hyperbola, the general points can be given in two ways. So remember, we're looking at the parametric form. Is going to sort of give us the points that we need to prove these results. So because a point or a general point on a hyperbola can be given in terms of sec and tan like this, or it can be given using a hyperbolic function. So using cosh and sine, it means that there are two ways in which we can either write the tangent or a normal. So let's start off with tangent, and we'll start off with a tangent using sec and tan. So tangent can be written as bx sec theta minus ay tan theta equals ab, or if we're using hyperbolic functions, it can be written as ay shine, whoops, I was actually going to write shine shine, that would be right, so shine t plus ab equals bx cosh t, and with a normal, again, that can be written using sec and tan. Actually, it becomes sine and tan. So for a normal, we'd have by plus ax sine theta equals a squared plus b squared tan theta, or if we're using shine and cosh, it would be ax shine t plus by cosh t equals a squared plus b squared, and then I need to squash in here shine t cosh t. So as I said, these results can be used without proof if you memorize them, but you could be expected to prove these results as well. Okay, so we want to find the tangent to this hyperbola here at this point, 6 to root 3. So the first thing we want to do is to differentiate. So what I'm going to do is I'm going to multiply through the whole thing by 36 so that I get rid of those denominators, just make it a little bit easier to differentiate. So I'll have 4x squared minus 9y squared equals 36. Using implicit differentiation, I'll have 8x and then minus 18y dy dx equals 0 when we differentiate the 36. So if I move the 8x over, so I'll have negative 8x, and then divide that by negative 18y, I finish with dy dx equals 4x over 9y. So notice this is one of those where you need the x and the y coordinate to get the gradient. So now we'll put in the coordinates. So at x equals 6, y equals 2 root 3, we'll just substitute that in. That will give us dy dx equals 4 times 6 over 9 times by 2 root 3. So let's just do that now on my calculator. That's basically 24 divided by 18 root 3, and that gives me 4 root 3 over 9. 4 root 3 over 9. So there's my gradient. I don't need to change it because it's a tangent, not a normal. So now I'm going to use y minus y1 equals m x minus x1. So that will give me y minus y1, which is 2 root 3, equals m, so 4 root 3 over 9, x minus x1, which is 6. Right, let's expand the brackets and move the 2 root 3 across. So I will have 4 root 3 over 9 x, then minus 6 times 4 root 3 over 9, and then plus the 2 root 3. So I'll have a final answer of y equals 4 root 3 over 9. Now let's work out what this 24 root 3 over 9 is. So 24 times by root 3 divided by 9, okay, which is 8 root 3 over 3, and then plus 2 root 3. It gives me minus 2 root 3 over 3 as the equation for my tangent. Show that the equation of the tangent to the hyperbola with this equation here at this point, so that's using the hyperbolic version of the coordinates, can be written like this. Now this was a result that I gave on the first slide, so as I said, you can be expected to prove it as well. Okay, so we're going to have to use parametric differentiation. So if x equals cosh t, then not dy, dx dt, so used to writing dy dx, is going to be a sine t, and if y equals b sine t, then dy dt is going to be b cosh t. Okay, so you should remember those results from the hyperbolic functions chapter in core 2. So dy dx using parametric is going to be dy dt, which is b cosh t, over dx dt, which is a sine t. So now, like before, we use y minus y1 equals m x minus x1, where this is where we'll get x1, y1. So we'll have y minus b sine t equals m, which is b cosh t over a sine t, times by x minus x1, so that's going to be a cosh t. So the rest is just multiplying and rearranging. So we're going to multiply both sides by sine t, or a sine t. So that will give us a y sine t minus AB sine squared t equals, and then we'll expand the brackets as well, bx cosh t minus AB cosh squared t. Now if we move the sine t across, so we have bx, we're trying to get it in the form that they have, so we've got bx cosh t, then it will be minus ay sine t. So when we move that across, that'll give us AB cosh squared t minus AB sine squared t. Now this is an identity. Now I don't know if you remember from the hyperbolic functions that cosh squared t minus sine squared t is equal to 1, or equivalent to 1. Now if you can't remember that, if you start with your sine squared plus cos squared is 1. Remember, you can use Osborne's rule to get from a normal trig identity to a hyperbolic identity. And Osborne's rule says if you've got this implied or obvious here product of sine, you replace it with like the negative version of that. So you take your normal identity, I've got a product of sine there, sine times sine, so you replace it with the negative hyperbolic function to get from a normal one to like a hyperbolic one. So anyway, what will happen then on this side over here, this can be factorized, so you've got AB cosh squared t minus sine squared t, well that's 1, so we get the result as required. So I need to write this out over here, minus ay sine t. So final result, bx cosh t minus ay sine t equals AB as they require. Okay, so in this question, show that an equation of the normal this time, of the hyperbola with this equation and these general points, okay, which is basically the parametric equation there, gives you this. So this is what we want to finish with. So it's very similar to the last one. So the first thing is that x equals a sec theta. So using parametric differentiation, we're going to find dx d theta. Now if you can't remember what sec theta differentiated it is, it's not a problem, it's in the formula book, but it gives you sec tan. Thing is, when you've done lots of these questions, you'll probably begin to remember what they are, and you'll probably know tan because you've done it so many times. So dy d theta, tan differentiated becomes sec squared. Okay, so we want dy dx, so we're doing parametric, so that's going to be dy d theta, so b sec squared theta, over dx d theta, which is going to be a sec theta tan theta, and I can see straight away that this sec theta is going to cancel out with one of these, so that just leaves b sec theta over a tan theta. Now this can be simplified even further, because remember sec theta is the same as 1 over cos theta, and tan theta is the same as sine theta over cos theta. So if we're doing sec divided by tan, we're basically doing, let's write it over here again, 1 over cos divided by sine over cos, or times by cos over sine. So here the cos's cancel out. So all of this here just becomes 1 over sine. Obviously the b and the a are still there. So 1, so just left with b over a sine theta. So the gradient simplifies, or the gradient function simplifies to this. So now we use y minus y1 equals mx minus x1. So y minus y1, b tan theta, equals m. So that's b over a sine theta. X minus x1, which is a sec theta. I just spotted something. I'm doing a normal, so I've got to flip that over. I'll put a little note here as well. So this should have been a sine theta over b. Okay, so I'll just put here and put a minus sign in as well. So stick a minus there. So don't forget, like I did, don't forget we need gradient of normal, and the gradient of the normal is going to be negative a sine theta over b, a sine theta over b. Okay, so let's make this a bit better. So I've got a bit more space to put my minus sign in, or my negative sign. So negative a sine theta over b. Okay, so from here we'll multiply everything by b. So we'll have by minus b squared tan theta equals, then we'll expand the brackets, so negative ax sine theta plus a squared sine theta sec theta. Now you may have spotted this, sine times by sec, well that's just tan, because basically what you've got is sine times by 1 over cos, so that's tan, so that becomes tan. Now what I'm going to do is also move the tan over, the other tan over to that side, and move the ax, so it becomes plus ax sine theta to this side, and then on the other side I'll have b squared tan theta plus a squared tan theta, which of course I can factorize, and that'll just give us the final result, by plus ax sine theta equals, well it could be b squared plus a squared, or a squared plus b squared, doesn't matter, tan theta. So we've proved that result as they require. Okay, so we want to show that the condition for the line y equals mx plus c to be a tangent to the hyperbola with this equation, that m and c must satisfy this equation here. Okay, so that means putting this into here, and if it's going to be a tangent, that means when we put the two together and we get a quadratic, we want to check that the discriminant equals 0, which means one solution. And one solution means a tangent. If it said chord, then we'd say that it have two solutions, and it'd be b squared minus 4ac is greater than 0. But since it's a tangent, that's what we want. So you've got x squared over a squared minus, replace the y with mx plus c, all squared over b squared equals 1, multiply both sides by a squared and b squared, so I'll have b squared x squared minus a squared mx plus c, all squared equals a squared b squared. Then we'll expand the bracket, so we'll have b squared x squared minus a squared, and then in brackets we'll have m squared x squared plus 2 mcx plus c squared equals a squared b squared. Now I want to multiply this all out because I need to find the coefficients of the x squared and the x and a number. So I've got my a, b and c for the discriminant. Right, so b squared x squared minus a squared m squared x squared minus 2a squared mcx minus a squared c squared, and then minus a squared b squared equals 0. So if I write it, so I've got the coefficient of x squared all together, so that will look like this, because these are my x squared terms. I only have one x term, so that coefficient would be, so it's plus, and if I do it as minus 2a squared mc x, and then the number I write as plus, or plus a squared c squared minus a squared b squared. Right, so I now have my values of a, b and c for the discriminant. So a in the discriminant is going to be b squared minus a squared m squared. B in the discriminant is going to be negative 2a squared mc, and c in the discriminant is going to be a squared c squared minus a squared b squared. Right, so let's do that then. So now we're doing the b squared minus 4ac equals 0. So b squared, so that will be negative 2a squared mc all squared as my b squared minus 4 times a, which is this, times by 4ac. I've done c, haven't I? 4, so I've got 4ca, doesn't matter. It's all going to be multiplied out the same way. So I've got b squared minus 4ca, but it's the same thing, equals 0. Now, just like when I did the one with the ellipse, I'm going to take out a squared as a factor of each term, but I need to think about what this first bracket here is going to be like when I expand it. So that will actually be 4a squared, or a to the power 4, m squared, c squared. So I'm interested in this really taken out as a factor because I'm going to divide by that in a minute. And then minus 4a squared, so I'm taking it out of a factor of this first bracket there, so you can see the a squared here's gone out to the front, times by the b squared minus a squared m squared. So I can divide everything by a squared, so there and there, and I can divide everything by 4 as well, there and there. That leaves me with a squared m squared c squared minus, and now I'm going to expand the brackets as well, b squared c squared minus a squared c squared m squared, then minus b to the power 4, then plus a squared b squared m squared equals 0. Now the a squared m squared c squared is going to go because we're subtracting it from here. So we're almost there, we're not far off. I think I'm going to have to multiply by -1 at some point. But I've got minus b squared c squared, then minus b to the power 4. And then let me move the a squared b squared m squared to the other side. So actually, if I now divide both sides by negative b squared, then what I will have left will be b squared, that's from the second term on the left, plus c squared equals, on the right hand side, remember, divided by negative 2, so it then becomes a squared m squared, and we've proved it as required. Okay, so this time it says the tangent to the hyperbola with this equation here, and at this point, parametric, crosses the y-axis at the point 0, negative 1, find the value of t. Now we're going to assume that we've remembered what the formula is for the tangent of a hyperbola, and we're going to use it. Now if you don't remember it, then you're going to have to take these parametric points here and differentiate them to find dy dx, and then use that to find the equation of the tangent with this point. But if we can remember what the formula is, and I'll write it down here, it will save time. So for a tangent, remember, for hyperbola, it's going to be ay sine t plus ab equals bx cos t. So we need, first of all, a and b to put in there. So from the equation and from the points as well, you can see that a equals 3, b equals 2. So they can be put in. So we have 3y sine t plus a times b, which is 6ab, equals b, so 2x cos t. So we're told it passes through the point 0, 1. So at x equals 0, y equals, did I say 1? I meant negative 1. So we'll have 3 times by negative 1 times by sine t plus 6 equals 2 times by 0 cos t. That makes it much easier. So then we have something like minus 3 sine t plus 6 equals 0, which gives us sine t, if my maths is correct. Take away 6 from both sides, which will be negative 6, and then divide that by negative 3. So we've got sine t equals 2. Now you might be tempted to do the sine inverse on your calculator, but it's not going to give you an exact answer. And actually we can use the formula book. So if we do arc sine to both sides, we'll get t. T is going to be equal to the arc sine of 2. Now if we look in the formula book, it actually tells us how to find the arc sine of something, and you'll find in the formula book that if we want to find, and there shouldn't be a c here, just arc sine. So yeah, if I want to find the arc sine of something from the formula book, then it tells us that it's the log of, natural log of x plus whatever that value is, x squared plus 1. So you'd probably expect a question like this to say find the exact value of t, because your calculator will give you like a decimal value of t. And if you want to do the inverse hyperbolic functions on your calculator, then you'll have to press the option button, and then the first option you'll get, say, hyperbolic functions, and then it will list them there. And sine inverse, I think, is for arc shine. And yeah, a calculator will give you something like 1.4436. But yeah, we want the exact answer. So t will equal the natural log, and we could probably even give our answer exact as a natural log, 2 plus the square root of 2 squared plus 1. So we can give the exact answer as log 2 plus root 5. Okay, so we have a hyperbola with this equation. The line L1 is a tangent to the hyperbola at this point. The line L2 passes through the origin and is perpendicular to L1. So if we can find a gradient of L1, we can find a gradient of L2. L1 and L2, these two lines intersect at the point Q, show that the coordinates of Q are this long thing here. So the first thing that we're going to do is we want to find the equation of this tangent. Now we're going to do it the quick way, which does mean that we need to memorize the form of the tangent in the hyperbolic form. Okay, now if you don't remember it, then you can still find the gradient by doing parametric differentiation with this and just doing y minus y1 equals mx minus x1. It will take a little bit longer, but yeah, it does help if we can remember. And for a tangent, I'll just write it here. It is AY shine T plus AB equals BX cosh T. So it is worth remembering because it will save time, right? So in this question, A is 6, B is 3, so we can just substitute that in to get the equation of L1 as 6y shine T plus A times B, so that's 18, equals BX, that's going to be 3x cosh T. Okay, so that's our equation of L1. We're just going to rearrange it so we get it in the form y equals mx plus c, so we can easily get the gradient of L1 and then we can use that for L2. So if we make y the subject, that means dividing both sides by 6 shine t and taking 18 away from both sides. So we'll have 3x cosh t divided by 6 shine t minus 18 divided by 6 shine t. Okay, so a gradient of L1 then, gradient of L1, and I might tidy up L1 in a moment, is going to be 3 over 6, so it's a half times by cosh t over sine t. So basically it's cosh t over 2 shine t. So as I said, I'll tidy this up a bit. So we'll get y equals cosh t over 2 shine t x minus, and then it'll be 3 over shine t. Okay, and we'll probably need that a little bit later. So now we can use this to find the gradient of L2 because it's perpendicular. So gradient of L2 is going to be that whole thing flips over, so 2 shine t cosh t. Now since L2 goes through the origin, then the equation of L2 is just going to be y equals oh, and we need a minus as well, almost forgot about that. So gradient over L is going to be negative, is going to be, yeah, so this is the equation of L2. Yeah, because obviously x1 and y1 are 0. Now since L1 and L2 intersect, we can put them together to find Q. So x coordinate of Q we'll find first. Of Q we can find by making L1 equal to L2. So that will be cosh t over 2 sine t x minus 3 over sine t equals, so that's L1, equal to L2 minus 2 sine t over cosh t x. Well, I need to get rid of both of these nasty looking fractions, so I'm going to times both sides by 2 sine t and times both sides by cosh t. That will get rid of these fractions that we've got. So then I will end up with cosh squared t minus 6 cosh t equals minus 4 sine squared t. And I mustn't forget I'm going to actually have an x here. Looks a bit like a power. Actually, let me write this out again and put the x's in. So yeah, so cosh squared tx minus 6 cosh t equals, and then minus 2, sorry, minus 4 because I'm multiplying by 2, so minus 4, it's going to be a bit of a squeeze, sine squared tx, just about fit that x in there. Right, so from there I'm going to move the x terms to the same side so I can factorize it. So I'll have cosh squared t plus 4 sine squared t. They will be x equals 6 cosh t. So that will give me an x coordinate, an x value of 6 cosh t over cosh, let's write it the same way as they've written it, so 4 sine squared plus cosh t. Okay, so we're halfway there. So we found the value of x. So now we need to find the y coordinate, which is just a matter of substituting that x coordinate into the simplest looking equation to find y, and I'm guessing that the easiest way to find y is to substitute it into here. If we multiply the x coordinate by this, we get the y coordinate. Okay, so y equals the x coordinate 6 cosh t over 4 sine squared t plus cosh squared t times by this bit here, which is basically the gradient of the L2, so times by negative 2 sine t over cosh t. Now what does that give us? Well, I can see that the cosh t's here will cancel out. There's nothing that cancels out the other way. So the 6 times by negative 2 is going to give me negative 12 sine t over, well, it's going to be the same denominator as the other one, isn't it? 4 sine squared t plus cosh squared t. So Q equals 6. This is probably one of the biggest fractions I've ever written. Sine squared t plus cosh squared t, comma, negative 12 sine t over 4 sine squared t plus cosh squared t. We're almost there. As required. Okay, we should now be able to do exercise 3E on pages 82 to 83. And here are the equations here for the tangents and the normals if you wish to memorize them. Remember, they come in two flavors, two forms. One where the coordinates are given as hyperbolic functions, cosh and sine, and one where the coordinates are given as normal trigonomic functions, so sec and tan. So choose the appropriate one. Now, as I said before, you can get away by doing these questions without remembering these formulae, but it will save you a bit of time if you can get your head around memorizing these formulae here.